Everybody, hi. Again, Jim Malis here. I've got some people who are kind enough to be here. They're wearing masks to be here, so they're going to the mat for you guys, and they're trying to help you out. I'm trying to help you out, and we're all going to do good. We're going to do the best that we can do. For chapter 32 in Physics 210, Physics 210, chapter 32, 25, 27, 41, 45, 54, 55. These top 6 problems I already did. The quality of the recording that we had done on Friday, through nobody's fault, was just not that good. The audio wasn't that good. The video of it wasn't great either, and that's not the fault of anybody. It's just we'd gone somewhere else. It was a room. It was a whiteboard. There's still enough on there that I think it can help you. Let me give you the highlights of what's going on with this thing without completely redoing everything. Let me give you the highlights and then hit really hard 71 and 77 regarding this. So we talked about problem number 25 from chapter 32. And essentially, guys, for 25, they're asking a coil with cross-sectional area that is given to you, 1.50 times 10 to the negative 2 square meters and 225 turns, is positioned in a uniform magnetic field so that the plane of the coil is perpendicular to the direction of the coil. The time-varying magnitude of the magnetic field is given by B equals 4 minus 0.02 T minus 0.005 T squared, with B in Tesla and T in seconds. What is the EMF induced in the coil when T is this? Essentially, guys, like I said, we've done it. I did not like the quality of the recording, but it was good enough that I can still refer you to it. It's the video right just prior to this one, and we use this to actually get there. So we've got this, you guys. We're not going to worry about the magnitude of this necessarily. Depends on the question is being asked. But we do know that if this, and we said this last time, when something is spinning around, when we're talking about a varying magnetic flux, there is a lot that can be said. I mean, a flux can vary in a lot of ways. The B field itself can vary, or the area can vary, or both can vary, and the area that's being hit, so to speak. The area that's being hit can vary if the coil or coils are spinning somehow in a magnetic field. Then the effective area that's being hit is constantly changing, the flux is constantly changing, and there's an induced EMF and there's an induced current. Pretty important stuff. It could be that the area could change in some other way, perhaps. It could also be that the B field could change. Nature doesn't really know the difference. As long as there's a changing flux encountered, as long as the mathematics holds in all circumstances, as long as there's a changing flux, then it doesn't really matter. It doesn't really matter how it happens. If there's a changing flux, there's going to be an induced EMF, and it's as though, again, I can't emphasize that enough. It doesn't matter how the flux is changing. As long as the flux is changing and the mathematics is the same in all circumstances, the induced EMF is going to be the same in all circumstances if the mathematics comes out to be the same. Rather fascinating. Nature doesn't really know the difference. It's independent of the circumstances as long as there's a changing flux. This is what you're going to use. You're going to plug in all the appropriate numbers for it. You're looking to get, in this circumstance, okay, we can use the sign in there. When you plug everything in there and tie it, and T is 2 seconds, we end up getting, from using this, and again, it's in the other video recording, albeit not a great video recording, but it's there, and you should be able to see it. We're getting this. All of this, you guys, is in my notes. All of this is handwritten in my notes, and so you're going to see it in the notes too, but I figured I wanted to do this for you guys as well. That's 25. 27 is asking the question, a vibrating copper wire is magnetized so that it produces a variable magnetic field given by the following equation that they have in the book. Perpendicular to the plane of a 14-turn coil with cross-sectional area of 0.500 square centimeters placed nearby. How does the EMF induced in the coil vary with time? So, again, it's the same kind of argument that's taking place, you guys, and you just plug in all that's appropriate. Now, in this right here, coming back a little bit, in this particular case, let me just come right back here if I could. This right here can be written as negative N, and the flux is the product of two functional values, if you will. B could be a function, A could be a function. In this particular case, the B field is varying while the area is not varying. So I mean, we'd actually done something like this. If the area doesn't vary, you can take it out of the derivative. The area can be taken out of the derivative because the area is a constant in this particular problem. And it's coming out to something like this. I want to kind of emphasize that. That's done in the notes, as I had already said. It's done in the notes, and it's also done on film the last time we were together. So you can kind of go here. The same kind of argument is taking place. Let me just see that really quickly, guys, if I could. I want to mix you up here more than I already have. Yeah, that should be fine. So with this right here, that's the reality here. The same reality is going to hold for 27. And that is, you're saying that E is negative N same kind of argument. So we got this. So far, so good. As we proceed, they're essentially telling us that the area is not really what's varying here. So you can bring this out again, and you can kind of say, well, the B field itself will vary, but not the actual coil itself. What's going on there is not really going to change much. So we're looking again at a situation where you're going to set it up as negative D. The area doesn't change, and you've got dB dt to actually do that. They gave us an equation around which that's all done. And they're telling us, first of all, there's 14 terms. And they're telling us terms, and the area is 0.5 times 10 to the negative 4. And let's see exactly where we're going to go from there. So that they gave us this. We figured out this was in square centimeters, and we converted square centimeters to square meters. Remember, 1 square centimeter is 1 times 10 to the negative 4 square meters. How does that work? Well, 1 centimeter by 1 centimeter is a lot of things. 1 times 10 to the negative 2 meters times 1 times 10 to the negative 2 meters, and we're getting this. So the 5 square centimeters is multiplied by this, and you get, or the 0.5 square centimeters is going to be 0.5 times 10 to the negative 4 square meters. They gave us the B field, for which I've got to do this. So if that's the case, if they're telling me that, you guys, we can say dB dt is going to be d of, and they told us it was 25 minus 1.55 cosine. This is the functional value. It's in radians. We said radians are the lingua franca regarding angular measurement. The derivative of constant is 0. The derivative of this, well, it's going to be negative 1.5 times the derivative of the cosine, which is negative sine. Negative times negative is positive. going to be sine this. Don't forget, by the chain rule, you got to multiply by this too. And so on and so forth. So you're going to plug that right into here. The value that you got for that, you're going to plug in right here. That dBdt. Plug that in right there. That's it. You're going to grind it out. This is positive, that's negative. The answer is going to be negative. We ended up getting, forgive me here guys, I'm going to be using chalk all over the place, I think. Did not sound good. Believe me, that hurt me more than it hurt you. Okay. 0.2284 sine, after you grind everything out, the sine is still there, it's going to vary. That means the E field's going to, that means the electromotive force is going to vary. Yes, if the flux is changing, constantly changing, the EMF is constantly going to change. If the electromotive force, if it's a variable quantity regarding the flux, if the flux is a very strongly variable quantity, as this is, the EMF is going to change strongly. So that was 27. So that's good. I mean, as we proceed. Let me look at, again, this is stuff this is all in the notes, you guys. I don't want to go from start to finish. I'm hoping what I did the last time when I was working in another room, despite the poor quality of the recording, you've seen it, you got enough there that you can look at it, should be legible enough, though I can't be heard that easily, and I'm a hard guy not to hear, but you should be able to hear something on it enough, and now I'm just going through it again to show you. All of this, in addition to what I said, and I've been saying it a bunch of times, guys, this is all in your notes. This is all in the stuff that I've already provided for you. All right, that's 25 and 27. Let's keep going. 41 and 45. What they're saying here, for both of these, give you kind of like the argument for what's proceeding here. Now here they're talking, it's the same argument, guys, all over again, and we said, it's, this is kind of the bread and butter for a lot of what you're going to be seeing. Oftentimes the negative, you can argue its significance. I mean, there is significance there. I don't want to belittle it completely, but the magnitude of what is going on, and the negative just tells you the induced EMF produces an electromotive force, produces a potential difference. The changing flux produces an induced potential difference that opposes the original flux that was being imposed upon it. So this is just like, and that negative just kind of gives you the bookkeeping for that. The changing flux, the rate of change of the flux, and everything else pertaining to it, the rate of change of the flux and the number of turns is directly proportional to the induced EMF, to the induced potential difference. The induced potential difference will be something that would induce a current that would produce a flux that would oppose the flux that's initially imposed upon it, and that's why they've got the negative there. They're doing the same thing here, guys, with 41 and 45. A generator spinning at a rate of 1.20 times 10 to the negative 3, a generator spinning at a rate of 1.20 times 10 to the 3 revolutions per minute produces a maximum EMF of 45 volts. At what angular speed does this generator produce a maximum EMF of 64 volts? Well, my gut tells me if you want to get it to a maximum of 64, and earlier the maximum was 45, and if that's the case, and we're saying that the B field is the same in both circumstances, you can do a lot of stuff here. I mean, you could say you could actually just look at the two different Emaxes. There's an Emax and an Emax. I believe with the notes I called one of them 1 and the other one 2. One is on top. If you're gonna look at that situation, do you got any comments on what we can say? Well, I'll tell you, we can look at it and we can figure out what they're saying. I think the best way, again, sound like the broken record. You have this in your notes, and I did it last time. But like I said, I was a little less than pleased about how things had gone, but they're basically saying to you, if you're, however you talk about this kind of stuff, if something's spinning like that, the E is going to be, negative N d5b dt. Wow, it's starting to sound a bit like a broken record. And that's going to be negative N D, and B and A are potentially classic variable functions. They both can be variable. They don't necessarily have to be variable, but they can be. So, yeah, this is not, it's going to be in the way it all goes up. So, looking at this, we have a situation like this. I got to run and get more chalk. We'll get more chalk. That's no problem. So you're looking at this and we're saying, okay, well, the B field ain't going to vary. I mean, they're keeping it pretty much constant. If that is the case, what's the rate of change of the area? So let's get a little on the interesting side. Well, let's take a look at this. I mean, we could say that's the same. Let's say a bunch of things here, I guess. BA is BA cosine theta is really the better way to have done it. So forgive the alteration here, guys. Cosine theta right here. Let's make it like that. And theta is omega t. The B ain't changing. Take it out. A doesn't change either in this case because it's the maximum area times the cosine function. The cosine function allows the area to become variable. They're treating A as they're treating B and A as a constant here, and the omega, cosine omega t is what allows the effective area in contact with the B field to vary. So with that in mind, let's deal with it. You got negative NBA times negative omega sine omega t. And that's where they're getting the derivation on all this. So at the end of the day, when they're doing this, negative times negative, negative times negative is positive, omega NBA sine omega t. So, and again, different ways you can write that. You could put the omega. Anyway, the order of the multiplication is irrelevant. Everything is fine in that regard. Doing this, you can compare the two. So this is NVA omega 1. They want it, now what am I doing here? They want the maximum. What is the maximum value you can attain for E? The maximum value is constant, 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 constant. Sine omega t does all the variation here to make the induced EMF occur in the first place. The biggest value that the sine value can have is 1. If it's 1, then it's omega NBA, or NBA omega. So it's the same number of turns, same B field, same maximum area, but one's got an omega 1, one's got an omega 2, and that really runs the show, you guys. Max divided by max, I think we're talking about for this one, well, let's just, we can do a bunch of stuff. You can see it here, you can say E max 1 over E max 2 equals omega 1 over omega 2. And what does that mean? Well, it means I think we already know what it means. I mean, at this point, it's going to be 64 is the new max that you want, 64 for an induced EMF, as opposed to 45. Well, what would the omega be associated with him, the omega 1? What would the omega be associated with the other? It's 1200 revolutions per minute. Here, I do not need radians. Here, I do not need radians, you guys. I can use radians per second, I can use radians per minute, I can use revolutions per second, revolutions per minute, degrees per second, degrees per minute. It doesn't matter. Why doesn't it matter? Because all the laws hold regardless of units as long as there's a valid comparison. Remember, oftentimes you can't do that. I mean, you really got to watch out when that's occurring and when not. Whenever in doubt, make everybody under radians. But since here, if I'm comparing the height of two buildings, and one of the buildings is 500 new units, and the other one's 250 new units. I don't know what a new unit is. I do know this much though. 500 new units is twice as big as 250 new units. And the ratio there will hold. It'll be 2 to 1 when you're doing something like that. So you play this game like that, you do cross multiplication. You guys know the song and dance. Like I said, I did this, and what do we get? I mean, at the end of the day, it's going to be a bigger amount of revolution going on. It is 1706.67 revolutions per minute. Can you make that revolutions per second? Can you make that radians per second? You can make it just about whatever you want. Again, when there's a comparison like this and things cancel, revolutions per minute divided by revolutions per minute is unitless. Volts divided by volts is unitless. It works. It doesn't matter. It doesn't matter. Okay, so that is what was going on with that one for 41. For 45, they're kind of asking a similar thing here, guys. Right? Like I said, we already had done it, but like I said, I want you guys to kind of, there's an A and B on this one. The magnetic flux through each turn of a 140 turn coil is given by phi sub B is 8.75 times 10 to the negative 3 sine omega t, where omega is the angular speed of the coil and phi B is in Webers. At one instant, the coil is observed to be rotating at a rate of 8.90 times 10 to the 2 revolutions per minute. A, what is the induced EMF in the coil as a function of time for this angular speed? What is the maximum induced EMF in the coil for this angular speed? Okay, so let me just try to give you a little bit of a feeling for that in the repetition here. Like I said, when I go through 71 and 77, we'll go a little differently when we do it. So let's see what we can say here regarding that. Okay, basically, guys, they're doing the same stuff they used to do. They are that's okay, Christian, right? You're okay. Okay. We're talking about 45. We're going back to the bread and butter, you guys. Bread and butter here. It's looking like that. Okay, let's just do what we know how to do. They told us it was 140 turns. We are getting the derivative of what they gave us, and they said it was 0.00875, the way they said it. And the other thing here is sine omega t. And that's it. I mean, the rest is it's just, some old-fashioned math when you do it. You take the derivative, do the chain rule, be careful. We had done that last time. Let's see where we are. Guys, I got all this different chalk here. I just want to make sure I can erase it. I don't want to end up... Oh, no, we're good. I keep going. Thank you. So we're doing this. Take the derivative of the sine function. What is it? It's cosine. So the derivative of sine omega t is omega cosine omega t, and the song and dance that we usually have to do. So at the end of all this, you are talking about negative 140 omega times 0.00875 cosine omega t, whatever that's going to be. Let's just make sure we're on the mark here. Yeah, it looks pretty good. Christian, can you go lower? You can get all this on the bottom too? Okay. And so what we got here is, let's see here, it's looking pretty good. All you do is you plug in the appropriate values on this thing, you guys, and see where you want to go. So we set, we they told us it was, I think it was 8.9 times 10 to the 2. 8.9 times 10 to the 2 is 890 regarding revolutions per minute. You divide by 60, you get revolutions per second. You multiply by 2 pi. Let me talk a bit about that, if you don't mind. All right, okay, guys. So let's continue. Basically, what we're doing here, guys. We got to here. We said this for 45. I don't want to beat this thing to death. Like I said, you guys got it. You're going to hear me say this a bunch of times. You got all of this in your notes. So if I'm not making sense, look at my notes. Maybe my notes make sense. But you're getting to here. We know they're telling us omega is 8.90 times 10 to the 2, something along those lines. That's revolutions. 8.9 times 10 to the 2 revolutions per minute. If you divide by 60, that's revolutions per second. If you multiply the revolutions by 2 pi, you get radians per second. And that's really the one they like to use when everything is straight out happening there, guys. So you got radians per second here. Omega is this, so it's 93.2 radians. Radians per second. Okay, we know that. It's a good question in its own right, I guess you could say. What's going on? How do you want to discuss the EMF here? Well, didn't we say E was equal to negative N times d phi b dt? Negative N is negative 140 times, so there's a bunch to be said here. Let's just write it this way. When you plug this omega into here, you've got the function. I mean, you already got the function. It's right here. There's no real mystery right here, guys. We already got this function. Okay, guys. So, as we said, this runs the show. This is it. You plug everything in here, you're done. The whole thing's done. You plug in the omega in here, and you're done. So, you look at this, and when I plug in everything, you guys, I do all the wheeling and dealing that I got to do. Remember what we said omega was? Period. End of the story. This is the variable way to look at this thing. When this guy is equal to 1, you're going to get the max. Hell, if you want to make it equal to negative 1 times negative this is going to be 114.17 as far as magnitude is concerned. So when this cosine right here, when this thing right here is equal to 1, you got the max. The absolute value of that max is 114.17. So for B, the E is going to equal E max is going to be 114.17. Who's negative, who's positive, who cares? What's the maximum going to be? If this is a negative 1 and that's a negative 114.17, negative times negative is going to get you there. Now for 54 and 55, let me try to make them one big conglomerate. Look at this. I all did last time, guys. It should be visible. If it ain't, hopefully what I'm about to do is going to make it a little bit visible for you. The big thing here, you guys, is look at the notes. Okay, the big thing is look at the notes. Arguably, I mean, you could say, if you're really comfortable with this, I've had people tell me, Jim, I mean, we're fine. We just look at the notes and we're good. So I think we're okay, but let's do a little bit of this and let's see what we can do. As long as they haven't shut down everything yet, right? I mean, they haven't, so we'll do what we can do. So 54, 55, there's two things here. They want you to find the average of one of those functions, and they want you to find the average of the other function. So there's two different functions here over one period, and they want to tell you some things. Let me put 54 and 55 sort of together. Let me go over there a little bit, and we'll see what we can say here. So before we do, let me go over there. Might be a little more room for us, I guess. So guys, what we got, there's a lot more here that meets the eye, I guess you could say. as with so many things, I guess, right, in life. So let's see what we got here. They want to know the average. They want to know the average of this function. Well, how do you find the average of anything? Well, the average, you guys, well, the average of anything is you add a whole bunch of things together and you divide by the number of things there are. Add all the quantities together and divide by the number of quantities that are present to begin with. That's how you do an average. Well, it's hard to do an average if it's a continuous function and there's an infinite amount of quantities there. How do you do that? You do integrals. The whole situation here, for 54 they're asking this, and for 55, we try to give you a little bit of space here when we do this. Let's just do this. The general argument, you guys, is if you want to find the expectation value, you want to find an average. I'll put a bar over it if you want. How I do average. Average, expectation value, whatever, is the integral from 0 to 2 pi, in this case, of f of x dx divided by the run itself, which is 2 pi minus 0. You're running from 0 to 2 pi. There's a run of 2 pi, and this is the integral of this thing. So basically what you're doing is, for any kind of function like this, guys, and this is for both 54 and 55. So let's kill a couple birds with one stone, if you will. This holds for both 54 and 55. It holds for a lot of things, actually, and if you write it more generally, if that's from A to B, and this is B minus A, man, it holds for a whole bunch of things. If there was a function looking like this, and you wanted to find the average of that function, so let me write it a little differently, if you don't mind. Right like this, you got this, and you got this. I like to know the average of that function. I'm going from A to B. I'd like to know the average. For me, the average, my gut tells me that the average would be somewhere, I don't know, right about here. I'll tell you this much. If you ever found the area underneath here, find out the area of an equivalent rectangle. If you ever found this area right here, find out the area of a rectangle. And then this guy right here, that'd be the average. If you basically found the area, the area underneath that rectangle is the same as that area. Yeah, and that height right here, you're basically looking at a situation, you'd have F bar. I love this chalk. It doesn't erase to save its life, but it does write nicely, right? So you got, you've got this right here. You've got, okay, that's the height. B minus A is the length. And I'm telling you that is the integral from A to B of f of x dx. Sounds good to me. If this area equals this area, if this area right here, the rectangle's area, equals the area under the curve, then the average, which is this guy, the average height times B minus A, that length right there is B minus A. In terms of the length, that right there, that's B minus A. Right here. And that'll get you there. If you divide by B minus A on each side, so that's the argument to the whole process, you guys. You go integral from A to B of f of x dx over B minus A. Yeah, here's your B minus A. Here's the integral from A to B of f of x dx. It's the same argument. That's all that's going on here. That's what you're going to do for 54 and 55. So, with that in mind, I will erase that 45 over there, and that's what we had before, guys, and I'm just dealing with 54 and 55 right now. So I'm going to erase a little bit of this, too. Christian, don't worry if we didn't get it. It's okay. All right. So let's see what we can do here. We're going to do some things. Let me. I mean, it's a pretty straight move on this one, you guys. If you're going to do for 54, you're essentially just going. Give me the integral from 0 to 2 pi of the sine function dx. Divide by 2 pi minus 0, which is just 2 pi. You integrate the sine function, you get negative cosine function. So you got negative cosine from 0 to 2 pi. And the other one would be, that's fine. 2 pi minus 0 is just 2 pi. If you put 2 pi in here for the cosine function, you get 1. If you put 0 in there, you also get 1. So you basically got, the negative, it's just going to be the negative of the negative of the cosine function at 2 pi, which is 1. The negative of the quantity, 1 minus 1 is what it is, guys. I'll kind of make a long time, I'm not saying this that well. You block that off and you just put 2 pi in for the cosine function, you get 1. If you put 0 in for the cosine function, you get 1. You're getting 1 everywhere. You're getting the same thing both places. Two things that are the same, when you do subtraction, you get 0. That's kind of the moral of the story of the whole thing here. You got 2 pi right here. It's going to be 0 divided by 2 pi. It is 0. The average of the sine function is that. So what's going on here? What's going on here? Well, I mean, I think what's going on is I can say it's obvious, I think it's obvious, if we look at it carefully. You gotta be careful when you say something's obvious, because I don't think anything's obvious in life. Not too many things are obvious. But let's give it a look. I mean, give it some kind of a look. If you're gonna say the sine function is the f of x, it's looking like this. This is 2 pi, this is 0, and maybe it is obvious. Maybe some things are obvious, I guess. Some things are obvious. This amount of water that can be held here is the same amount of water that can be held here if it was flipped upside down. Everything here is the same as everything here, only if you'd have to multiply every single item here. Every single function here, if you multiply it by -1, you get what's over here. It's about that simple. Every single one of them, multiply by -1, you get this guy. It's completely symmetric. On average, yeah, it's 0. If I integrate here, I get a positive area. Here I get an area that is negative of the same magnitude. Negative magnitude area and same magnitude positive area added together, negative and positive of same magnitude each one with one another. If I add these two equivalent areas, but one of them's negative, one of them's positive, same magnitude though, negative and positive is going to be 0. We're talking about same magnitude. That's all they're saying there. They try to pull something here. I got it in more detail on my notes, guys, when we get to 55. I got more detail for you guys there on that one. And there's ways you can kind of deal with some of the trigonometric functions. I'm not going to go there right now, but I invite you to go there in my notes if you choose to go there. E to the I theta equals cosine theta plus I sine theta. Right now, it's pretty beautiful mathematics. You guys have heard me say this countless times. The mathematics behind all this stuff is surprising. It's initially, at first sight, counterintuitive. It's very beautiful. It works. And I invite you to take a look at it and some of the stuff we have done. In the mathematics of physics that I talk about in some of the notes, and in the actual problem we talk about e to the I theta equals cosine theta plus I sine theta. We're not going to worry about that. Now, you can look at it. I'm going to take a little more of a intuitive approach to this other way to look at it. For this one right here, you guys, they're talking about f of x is equal to the sine squared of x. And now that's a little different dynamic. If you were to take this function and square it, it's going to remain positive here, and it's also going to, this is also going to be positive, looking exactly like this little mountain. There's going to be two little mountains like that, and they're going to be in the positive direction when you square it. So what happens is when you look at something like this, you're looking at, again, it's not going to be a great drawing here, and then you square the other one, bam, it touches here, and you're getting something like that. The crazy thing is, if you were to do that with, I don't want to call it the same thing, we call it something else. If you were to do that with the cosine, what if you squared the cosine function? What if you squared the cosine function? Well, the cosine function's got a little different look. I mean, cosine function, it does and it doesn't. What am I talking about? I mean, you got this, you got this, you got that. That looks a whole lot like the sine function. If you were to take what's going on with the cosine function, like this side right here, if you were to pick this thing up and go over to the right, this guy would slide over. It looked just like this guy. If I were to just, how many times have I told you guys? The cosine and sine function are the same size and shape, if you allow me to say that. It's hard to talk about size when something's infinitely long, but in any given interval, they are the exact same size and shape, they're just out of phase with each other. I can make them look identical to each other. If I take the cosine function right here, pick it up, and go pi over 2, 90 degrees, go pi over 2 to the right, this thing right here will go, whoa, and it'll look just like that over there. What does that mean? That means a lot. What it means is if you square this thing, you got a lot going on. I mean, let me kind of, so this is where it gets, you got to be a little careful when we're doing this now. I'm not counting him here, though I can later on. You know, I mean, I am going to do something with this guy later on. I'm going to move him over. But, so let's see what we got. We got this, and it's looking okay. Okay. Square this guy. Well, if you square him, now we just said it's identical. I mean, let's maybe, I try to think of the best way to do this. If you square this guy here, it's going to look, if you look over here, square him, it's just like him, only he's over here. Yeah, but if you move him over, forgive me, but if you move, but it becomes that. If you move over to the left, it's going to have basically this look to it. Let me just see here, guys, real quick. Make sure I'm doing this right. Bam, half. Okay. Tell you what I'm going to do. What do you say? You take this guy, cut him, move this guy over and paste this guy onto here. He's as big as this guy. It's the same thing. This whole thing, you're saying, okay, what are you talking about, Malus? I'm talking about this. Let's make a long story short. Let's take a scissors, cut the orange thing, glue it right here, and you got a mound and another mound. Move the mound over by pi over 2, you got this. I'll make a long story short. The area under this curve and the area under that curve are identical. You're going to get the areas under both. What does that mean? It means a lot of stuff. It means that if you take the integral from 0 to 2 pi of sine squared x dx, that's equal to the integral from 0 to 2 pi of cosine squared x dx. Fascinating. Interesting. Let's talk some more. Are you telling me that, so if you add them together, basically, well, let's talk. If they're equal to one another, then the integral from 0 to 2 pi of the sum sine squared x plus cosine squared x dx. Wait a minute, sine squared x plus cosine squared x. Sine squared x plus cosine squared x is 1. The integral of 1 dx from 0 to 2 pi is 1x evaluated between 0 and 2 pi. It's 2 pi. This is equal to 2 pi, which is equal to the individual integrals. Yeah, there's no short way to do this sometimes. You gotta kind of grind it out. It's equal to this plus this. These are equal. What does that mean? That means 2 pi. If these two are equal, then just call this guy, if they're equal to each other in terms of value, call this the integral from 0 to 2 pi sine squared x dx. And this is the integral from 0 to 2 pi sine squared x dx in terms of a value. That's 2 times the integral. 2 times the integral from 0 to 2 pi of sine squared x dx. Divide by 2 on each side. Well, it's a messed up song and dance, you guys, forgive me. Divide by 2 on each side, you got pi, there it is. That's pretty interesting. What's the average then? The average of the sine squared function, the expectation value, the average, so to speak, of the sine squared function, put a bar over it, right? The average of that is going to be the integral from 0 to 2 pi sine squared x dx over 2 pi, 2 pi minus 0. We just said this is pi. This is 2 pi. It's pi over 2 pi. At the end of that song and dance, the average value of the square is a half. The average value of that function over one complete cycle, from any cycle, in fact, that is, any cycle, that holds for any cycle. From 0 to 2 pi, the average of that quantity over any cycle is going to be 1/2. And that tells you something. You said that, it's going to, what does that mean? Well, that means if you're talking about some square quantity, let's say, the average is half as big as the max. What's the maximum of the sine function? What's the maximum of the sine squared function? The sine function gets its maximum value when sine is equal to 1. When the sine equals 1, the sine of x equals 1 is the maximum value you're going to get. Square 1, you get 1. So what's a half? Half is half as big as the maximum value you're going to get. So the average EMF accounting for sines is 0 for problem number 54, but the average, but the average for a different situation, when you're talking about power, is going to be equal to a half. Because power has a square term in it, and I talked about it a decent amount when we said it. So over each complete cycle. So you're looking at something like this when you talk about power, and you're getting an answer, as I said it last time, the notes, I think it's going to be visible, at least in the previous that I had done, the last time I had done this. We conclude that the average power supplied over every cycle is not 0. And there's additional ways to do it, and I show that as well, using e to the I theta equals cosine theta equals I sine theta, and so on and so forth. And it should be, like I said, it should be something you could see in the other recording, though the recording was not ideally to the quality we wanted. It should be okay. You should be able to see that as well. I'm just doing it again here. And then, of course, we draw the same conclusions as earlier, you guys, regardless of how you do it. So the power is going to have a square term in there, and so the average power is half of what the maximum power is when you're talking about power. Because when you're talking about power, it's V squared over R. And V has the idea of a sine or cosine function associated with it. So when you square that, you don't get the average over all the different, because the power is going to vary. There's going to be greater power at some points and smaller power at other points, but on average should be a half. This square right here means you're looking at the average of something squared, and that's a half. So generally the way they're going about this is that's what they're trying to say. So somewhere in here there's going to be something along the lines of, let me just actually quickly write it. There's a number of ways you can write it. But at the end of the day, you guys, you're looking at, when we're doing a lot of this stuff, let me erase this 54 real quickly here and go. Let me keep talking. Let me just go over here then. You're talking about power. We've said a lot of stuff. We said it's going to be V squared over R, or delta V squared over R. And what is that? Well, the induced EMF is the V, so it's NBA omega squared over R. NBA, all constants. R is a constant, omega is a constant. Interesting. And there's the sine omega t. Sine squared omega t. You're averaging the sine squared of omega t, you guys. That's where you're getting the half. And that's where the half comes out of there. At the end of the day, you end up getting 1/2. The average of the sine squared omega t. Remember what we said, the way the whole process took place. The EMF is the V, is NBA omega sine omega t. This is the initial song and dance to get you there. That's the initial song and dance to get you there, guys. You're using that right there, and if that's the case, that's what you're using. You're squaring all of this, and you get this. The R's here, and that's it. V squared over R. The end of all that is just 1/2 NBA omega, N squared, B squared, omega squared, N squared, B squared, omega squared over R. And that's going to be the average. And there's a lot, there's a whole bunch of ways you can do it. That would be the max. So this is half of the max. So what does it say about power? You're getting half the power out of there. This is why they like doing mathematics like this, because they can apply it to stuff.